Hello everybody. Today let us talk about relations, functions, and graphing these. So remember that algebra depends on a variable, right? Sometimes we have expressions with variables. Sometimes we call it x, let's say, and we're looking for it. Sometimes we say, solve for the variable, right, x, and so on and so forth. But now we can do something a little bit different, right? We take two variables, so let me get rid of that, okay? Two variables, x and y, let's say, and we can call them, x and z, alpha and beta, whatever, but let's call it two variables, two unknowns, two things that can change, to vary, right? Two variables, x and y, okay? And what a relation is, see this right here, relation, right? It's basically a relationship between the two variables. We were talking about x and y now. So relation, one way to think of it is a relationship, okay, between the x and y, okay? For example, a linear relationship. Let me do an example. So examples. You can have a linear relationship, meaning it follows, if you graph it later on, we'll see, you would get a line, and it goes in a linear, and if you increase one thing, the other increases by the same amount every time you increase that thing by the same amount. So linear, kind of the same thing to the same thing correlation. Yeah, you're going to have a slope, it's going to be linear, okay? A linear relation would be something like, oh, y is equal to mx, maybe like 3x minus a 2, for example. And so as x changes, y changes specifically based on how x is changing. See, so there's a relationship between the x and the y, equal sign between them, right? And it's not like I know what y is. I can't just solve for y, or I can't just solve for x, because I don't know two things, right? But if I know one of them, I know the other. They are related that way, okay? Maybe a quadratic, we have an x squared, right? Let's see, quadratic would be maybe, and let's kind of put it in a form that's not just y equals. How about this? X squared minus 3y is equal to 6, right? So some kind of relationship between the x and the y. Maybe another type, or we really will look into that, what in the world this is, okay, if you graph it. But how about x squared plus a y squared is equal to maybe 25. So again, there's a relationship between x and y. If I give you y as something, you know what x is, or a few values of x that can be x, right? Or the other way around. If I give you the x, the y has to be something or something, etc. All right, so relationship, okay, it's a relation between x and y, all right? And what's cool is that it can be kind of almost like a rule. So if we make, let's do this now. Let's call, what is a function, right? Let's go further. Let's go what a function is. Because function is actually a relation. It is a relation, okay? But more so than that. So a function, let's kind of underline this relation here, okay? It's an important word. Why is a function, a different word? Why not just say relation? Now a function, let me explain what that is. It is a relation also, okay? Relation between x and y, right? Between, let's say, two variables, x and y, where for every input, so you see now we have an input. We put something in. We start with something. Let me make it a little neater here. Okay, input, okay. We call it x, okay? Input of domain, so the variable x, okay? We get a specific, okay, we get one thing that we know what it will be if we calculate it, if we find it, a specific output of the range, okay? So the collection of outputs is called the range, so of the range, okay? These are big words, input, domain, output, range, of the range y, which is equal to the function value of x. So you put in x, blah, 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 you do the function, the rule, relations really, so it's another thing that we can make, another way we can think of it is, it is a rule, okay, that I always tell my students makes sense, okay? So in other words, what I mean by makes sense is that if you put in something, some kind of input x, you will be able to deduce what you're going to get, what the y will be. Okay? So an input yields a specific output, basically this right here. Specific is big. Okay? Versus, let's say you're saying, hey, you know, I'm in Houston, for example, and in 3 days, so like f of 3, and then you say, I have no idea what the temperature will be. Maybe it's 100 degrees, maybe it's 32 degrees, freezing, right, in Fahrenheit, or maybe, you know, whatever it is, and you don't know, really, the unpredictability. So I say, hey, you know, that's not a rule that really makes sense. That's not a function. Because I don't know if f of 3 will be 32, or f of 3 will be 100, or f of 3 will be negative something, right? But if I know f of 3 equals 100, in 3 days it's 100 degrees, guess what? Then it's acting as a function for that input. And if I know for all inputs, the outputs that there will be, or maybe like I know f of 3 and it just doesn't exist, that's fine, that there's no such thing, you don't use it even, the f of 3. And then it will be a function, okay? So it's a rule that makes sense, and it basically tells you what to do, right? And another way to think of it is, again, you know, inputs go to outputs, but let's go back, one relation between x and y, one thing we can also call it as is collection of ordered pairs. So for every x, there's a y, right? Or, you know, multiple, but collection of x, y ordered pairs, another way to think of it. So before we go even to function, a bunch of ordered pairs, x and y, is a relation. So let me give you kind of a more like a representation with numbers, a relation. Let's try an example and a function, actually. So let's try kind of some examples. Here's, let's say, a bubble, okay? And this is domain, okay, domain. So let's see, domain, and we put some numbers in, maybe numbers -1, 2, and 5, okay? And let's say we have a range of numbers, okay? Range. This is where we're going to get what we're going to get. And maybe we get from these numbers the numbers 3, -2, and 2. Somehow, some kind of numbers, right? So let's say that here we have a function, okay? It's a rule. It's going to tell us what to do. It's an operator, basically. It says blah, 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 do something, this, that, the other, and, you know, you're going to get, so here's the function. And let's say, for example, I'm adding 4. Well, okay, if I added 4 to the -1, oh, I'm going to get what? The 3, right? However, if I go from any other numbers, for example, let's say 2 in the domain, right? And I go and add a 4, it's going to be a 6, and that's a problem. It's not. We're not talking about 6. There's no 6 here. So the rule could not have been adding a 4. Maybe the rule is something else. Like, let's say, let me even think what it could be. So if, let's see, like let's say I doubled, I squared it, right? For example, and added 2. Well, that didn't work. How about I multiply by a -1 added 2? Well, that wouldn't work. How about a -3? Well, that wouldn't work. Yeah, let's do what's that? You see, something that would make it work. Let's see, how do we even make it? Let me show you a little trick. So you could do, oh, okay, let me figure out a linear one that would work. And I'm like, all right, so if a 3 is equal to some kind of slope, m times a -1 is x plus a b. See, I'm putting a -1, get a 3, and then let's say I want to get this 2. Let me kind of get back here to the red. What if I, just kind of a little side note here, what if a 2 goes all the way to a 2, right? So what if a 2 goes to 2? Well, maybe that would be right here that you would have that a 2 was the same m, and then if I'm doing linear, right, and 2 plus b. And so what happens is if I cancel these, I get a -1 is equal to 3m. So m is equal to -1/3, and b would then be what? It would be 8/3, and so 8/3 will equal to b, and you can check that for me. And so basically, if you have f of x is equal to -1/3 x plus 8/3, okay, that would make that 2 go to a 2 happen. right? Yeah, and that would make a negative 1 go to 3 happen. However, 5 would not go to a negative 2. Let's actually see what 5 would go to. But f of 5, you see, so linear wouldn't work here. Would equal to negative 1/3 times 5, that's 5/3 plus 8/3, and that's actually unfortunately going to a 1, right? So let's say if we change that to a 1, let's put a 1 here also, okay? And what I'm going to do is I'm going to say, hey, you know, here's a 5, and I'm going to take it from the function to the 1, okay? And then, you know, the negative 2, well, there's no negative 2. Can't get a negative 2 that way. And then this is our relation, and that, you know, y, this is a y if it's a relation, otherwise it's a f of x. So our function f of x is equal to negative 1/3 x plus 8/3 does this trick. F of x is equal to a negative 1/3 x plus 8/3 works, and may not be the only one, but for a linear, as linear function, okay? See that? It's kind of cool, right? So we actually found it, but again, we had to make sure that 5 went to also something meaningful. Okay, anyway, so this is a function because here's what happens, okay? You can even say domain. What's domain? It is, you can write it as a set of a negative 1, comma 2, comma 5. And then what's the range? The range of the numbers is the number, are the numbers, what is it? 1, 2, 3, right? 1, 2, 3. And we had, based on that relation, that negative 1 went to 3, 2 went to 2, and 5 went to a 1. Cool, right? And that's what you would do, okay? So that's how that works. This is a function because for every input, I know what I'm going to get, okay? So what it would not be a function would be if I know, hey, you know, 2 goes to 1 or 2, which is possible. What if 2, you know, somehow you squared a number, you know, for example, let me show you this way. What about an example of not a function? Here's an example of relation that's not function. Ready? Let me show you. Let's try this one. Y squared, okay, plus 4, let's do this, plus 4, let's do minus a 4x, let's say, minus a 4x is equal to 4. For example, right, some kind of, the equal sign, x and y going on. All right, well, what do we do here? Let me show you. For example, if, for input, actually what you do is you input x equals, let's say I put input x equals 0, okay? Then we have, what is y? We can find it. Let me show you. Y squared is equal to, well, what is that? Minus 4 times 0 equals 4. So y squared, right, that's a minus 0 equals 4, so it equals 4. And then y equals, and a lot of students will say, oh, it's a 2. Well, wait. Square root property tells us it's a plus or minus 2. So it could be negative 2, or y equals positive 2. So I don't know what I'm getting. That's not a function, okay? So which is it? Question mark, right? Not function. For example, already we found one that gives you not a specific output, because this is, or this, that's not specific. It has to be specifically something. So not a function. Okay, we found an example that's not a function. Now if you tried, let me show you. If you tried, here's what wouldn't actually help much. If x equals negative 1, watch this. Y squared, then we have y squared, let me make it a little neater here. Y squared is equal to, right, y squared minus a 4 times a negative 1, right, equals 4. Well, that means y squared plus a 4 is equal to 4. And that means y squared is equal to 0. Okay, y squared is equal to 0. So what is y? Y has to be 0. And so the problem is, this wouldn't help us because we are like, all right, well, this looks like a function. Think about it. Negative 1 went to a 0 specifically, right? But we know actually from the last example, the last like basically counter example, let me lower this a little bit here, that we had what? We had a 0, x equals 0 goes to a 2, or potentially a -2. And that was an issue, right? That we cannot have that. So that's where the error arises. Like, no way, right? This is kind of okay for a function, but problem is you have to have everything like that to make it a function. Okay, now let me show you something, another kind of insight that I give students sometimes in a verbal context, more like a like a word problem, whatnot. So another example of a function. Let me I think kind of silly. Okay, so let me tell you this. I have a dog by the name of Snickers, all right? And you may have some dogs, and so I ask students what kind of dogs they have. Let me show you. So let's have an input of we'll have dogs, hungry dogs. Well, I'll explain. So here's the idea. One thing also is we're gonna have a function, and we're gonna have an output, right? The range. We're gonna have the input, the output. So this function is dog feeder. So feeder, dog food, using dog food. Okay, nothing like, it's not like some kind of tasty anything besides. It's just we're giving dog food. And let me explain this. So here I am, and I'm like, hey, am I part of this domain? Am I going to get fed with dog food and going to become a happy whatever, Sergey, Dr. Sergey? Well, Dr. Sergey is not in the domain. I'm not eating dog food. All right, makes sense a little bit? I'm not somebody you're going to put into eating this dog food. So Dr. Sergey is not inside this domain. This is domain, okay? And I'm not in it. I'm outside there, okay? All right, you're not in it neither. I'm not going to feed you with dog food. You're going to break your teeth and maybe not enjoy it as much as, something else. Anyway, all right? Or people will make fun of you. Okay? Can you eat dog food? I mean, it's possible, right? Anyway, let's take Hungry Snickers, my dog Hungry Snickers. Okay? And he's always hungry. He's a chocolate lab, okay? So here's a Hungry Snickers. And let me take another dog. Let's say there's Rex. Let's say Rocky. A lot of students have different names. It's Hungry Rex, right? And then, okay, we're going to take Hungry Snickers. We're going to put him in the feeder function. Oh, guess what happens? He's going to eat the dog food, and probably more than likely, he's going to become a happy Snickers, all right? And this actually will bring us to a point that we actually will talk about much later on in class. Okay, it's called inverse functions, okay? And that being that when you go back on feeding the hungry Snickers, you basically unfeed hungry Snickers, whether that's animal abuse by squeezing him out, whatever, so he, vomits or gets rid of that food, reverse the process of feeding Snickers. Yeah, I know it's kind of silly, but really think about it that way. And he's going to become a hungry Snickers again, and maybe grumpy Snickers too, right? So if you go this way, and this was an inverse function, okay, right here, then you would get that hungry Snickers back. So that's just that would be inverse, F inverse function that we would talk about later in the class. Anyway, what about Hungry Rex? Well, we know that when Hungry Rex, maybe he's like some kind of bulldog, right? And he eats dog food, and then he's Hungry Snickers. Nope, right? We know what he's going to become. He's going to become a happy Snickers. He's going to become a happy Rex. So we said specific, right? Rex will go to Rex. It's just hungry to happy. And so this is another type of function, kind of, right? Am I putting numbers in? Am I doing, put a 4 in? No, 4 is outside. It's not in the domain. Domain is set of hungry dogs. I don't want to waste my dog food, so I'm not even going to put happy Snickers in there, or well-fed Snickers, because he's going to eat more and just going to get fat. Okay, so we're talking about hungry dogs right here. Domain of hungry dogs. Okay, or this domain, and what is this? It's basically fed or happy. It's called happy dogs, and what is that called? Anyone remember? It is called the range. Remember, range. That's the outputs that you can get. Okay, that's it. So that's an idea. These are ideas of functions, and let me show you one more example. Something I called. Remember, I told you graphing. So let me just kind of make this not too long of a video this time. But graphing, let me show you. Let's take a relation. All right. So relation, and I'm going to say, hey, graph a specific relation. Graph relation, and actually you'll see this is not a function for a specific reason. Graph a relation. And let's make a relation like this, x squared. So we're going to square the x, and then we're going to add it to y squared. And between them, the relation is that when you add the squares, it's going to equal to 25. Okay, so one way to graph it is to, first of all, what is graphing? It's a very beautiful tool invented about 400 years ago. We're not talking about 4,000, okay? This is a guy, René Descartes, a French mathematician, okay? And what he did was basically, hey, let's do this. Let's kind of put an input horizontal motion, like a real number line left, right, and then another vertical up, down motion for the y, okay? So René Descartes made up this rectangular, or Cartesian, after him, rectangular coordinate, talk about coordinates, right? X, Y pairs, coordinate system, also called Cartesian, and you can see Cartesian right there, right? So that's the idea. Let me actually underline that. Cartesian coordinate system, okay? Okay, and what that is that's where we're going to be graphing, right? That's going to be this X and Y axis type stuff, right? This is going to be this is a kind of rectangular, you move around rectangles when you plot points, right? So this is going to be our rectangular coordinate system, and this is going to be called, the horizontal one's called the x-axis, okay? It's when we're going to talk about the horizontal motions, the inputs cause it to do that, right? So you put an input in, remember the x is the input for, like, if you talk about a function, you can graph a function, or a relation. If you don't talk about x as an input, but just a value of a variable, x and y variables, the x is the horizontal, the first component you have an ordered pair, right? Like, let's say you have some kind of 3, -2. What does that mean? You go right 1, 2, 3, and you go down 1, 2. And that would be the point 3, -2. Anyway, let me erase that for a moment. And we are going to talk about this. Again, this is y-axis, okay? And we're going to graph our relation. Now, to graph our relation, it has to satisfy x squared plus y squared is 25. So let's try to graph it the best that we can, okay? And to do that, well, if x squared plus y squared is 25, okay? Remember, that's what it is, right? I'm going to make a little table of x and y values. Let's make it horizontal so we can see better this time around. Let me show you. Let's take out a line. Let's do a little kind of, just a little line segment there. And we're going to put in some values, okay? And, well, actually, usually you do a vertical, right? So let me kind of do that for us. Here's going to be like maybe a vertical. It's a little table, okay, with x and y values, inputs and outputs. So let's do this. Okay, here goes. Here we are. This is inputs x. This is, well, not inputs, but you put an x in, what the y is, or what the y is, what is x and the y is what. So let's say x is 0. Make it easy. Okay. If x is 0, okay, well, y squared is equal to 25, and y can be 5, right? Think about it. 0 squared plus 5 squared is 25. Okay. Or what if it's x is 0 and y is a -5? Remember, y is going to be plus or minus 5, right? So, okay, those are two possible values, and what does that mean? Horizontal on x, so there's no horizontal, it's 0, right? So I'll go no left, right, but down or up 5. 1, 2, 3, 4, 5. There we are. There's a point. Down. 1, 2, 3, 4, 5. These points we're graphing 2 points that satisfy our relation. Not random points, but these 2 points, the x and the y, are related by our relation. X squared plus y squared is 25. And so if 0, 5 works, then you put that point there. If 0, -5 works, you put that point there, okay? Let's do some more. How about x is a 3? Well, if x is 3, you get 9 plus y squared is 25. Subtract 9 from both sides. Y squared is equal to 16, and y can be plus or minus 4. So you get 3, 4. 3, -4 works, right? And what does that mean? Well, you go right, 1, 2, 3, up 4. Bump, 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 right there. You go right, 1, 2, 3, you go down, 1, 2, 3, 4, right there. We're getting more points. And similarly, you can get more points. What if x is 5? Well, 25 plus what is 25? 0. What if x is -5? Also, you'll get 0. What if x is a -4? Y can be 3 or -3. You can check that, okay? So check all these, and ultimately, you get these points. Let me show you. 4, 3, okay? 4, -3. 5, 0. -3 up 4, or -3 down 4, right? That's some points. What about -4 up 3? What about -4 down 3? And what about -5, 0? Whoops, right there. Right? Okay, and then guess what that looks like? Not a box even. What does that look like? You know what that looks like? You know what it really is? This is going to be a circle. Yeah. And what I mean by that is that not just connecting points randomly, but if you do any other x, your y's are going to be such that they're going to be lying on this, xy is going to be lying, and the points are going to be lying on this circle. And you can check that, even if it's irrational numbers, like square root of 21 or square root of something else, square root of 24. Okay? And so there's our circle. This is going to be a circle. Now, how do I know this is a circle? Because really, I mean, is it almost a circle, exactly a circle? Is it an ellipse? Is it kind of like some kind of weird, diagram, kind of, or some kind of shape that's really cool, some spiral? Well, let's see. Well, it's a circle, and here's the reason why. Let me show you quickly here, and that's going to be the last kind of thing we're going to do. So why is this a circle? Let me show you. It's really cool. You may like it. Let me show you this. So it's a circle because, why, right? Let me show you. Because there's a distance formula that's very important. Remember, what's the distance between 2 points? Let's say x1, y1, and x2, y2. We talked about it before. The distance is, it's like, we use the Pythagorean theorem. We never really proved it in this class, but I told you to remember it. It's something you have to know. In a right triangle, the a squared, let's call it delta x here, right? Change in x, plus the y squared, or the delta y squared, is equal to this, let's call this distance, d. So the base squared plus the delta y, the height, right? Base and height squared, is equal to the hypotenuse squared. This is the Pythagorean theorem. Okay? This is a really important theorem that was done a long time ago. I'm talking about more than 4,000 years ago. Okay? So Pythagorean theorem. Okay? And so named after Pythagoras, but it probably was even done before that. This is an Egyptian kind of theorem, so it says, by the name Pythagoras. But anyway, watch this. So delta x, the change in x, we go from x1 to x2. So look at this, x2 minus x1, right? That's how the delta x, right there, from x1 to x2. So that's, let's say your x2 is 10, and here it started at 3, then 10 minus 3 is 7, length, 7, right? And so maybe, plus say now, change in y is y2 minus y1 squared, and that's equal to distance squared. And so distance is equal to, if you do the distance formula, but we don't really need it here, but I'm just going to remind you the distance formula. Okay, what is that? That's d is equal to square root of both sides, and you can do plus or minus. However, here we just talk about the positive, right? Positive distance. And this is our distance formula. If you ever need to know how to prove the distance formula, that's it. Okay, but now let's go back to what our circle is about. If it's a circle, right, then we're talking about, here's the center, right, 0, 0, it looks like it's the center of 0, 0, and all the points, let's call this 0, 0, and this is a point xy, any point, right? What happens, now radius looks like 5. If this is a circle, everything will be 5. 5, 5, right? Radius is 5, radius is 5. Again, if it is a circle. But let's check, is it a circle? So if all the time radius is 5, the distance between the points, so distance between center, which is a point 0, 0 seems like, and any point on the circle, any point, well, we don't know it's a circle yet, right? But any point xy, let's say, is equal to the same, so that's what it is, the radius, right? Same radius equals 5. Let me write the word radius. Okay. Radius r equals 5. Then that's a circle if it works that way, right? Then it's circle. And let's see, is that what we have? Well, what is the distance between 0, 0 and xy? Well, we have the distance, and remember we already have the square, but anyway, let's do the distance. Distance is r equals 5, okay? And this is equal to the square root of, remember distance, right? Let's do distance is equal to, now r is equal to 5 is equal to x2 minus x1. Let's do the distance formula squared plus a y2 minus a y1 squared, okay? And that's going to equal to, well, x2 is this x, and y2 is the y, and the x1 and y1 are 0, 0. So let's do that with the square root of now x minus 0 squared, right? Plus a y minus 0 squared, Okay, that's just the square root of x squared plus y squared, right? Isn't that? There's no zeros to give away. And then square both sides, and we get what? X squared plus y squared, square both sides, square, and rotate, right? Flip both sides, square both sides. Okay, what happens? X squared plus y squared is equal to, what's 5 squared? 25. And that's exactly what we started with. I told you graph this relation. Okay, it's going to see that. So that is indeed a circle centered at 0, 0 with radius 5. All right, thank you for watching, everyone, and I hope this was informative.